Welcome to my presentation. My name is Stephan Kleber. I'm a PhD candidate at Ulm University in Germany. And I present to you our work titled Message Type Identification of Binary Network Protocols using Continuous Segment Similarity. This is work that I conducted together with Rens van der Heijden and Frank Kargl from the Institute of Distributed Systems at Ulm University. And the context that our work is located in is protocol reverse engineering. And probably the most famous example for this is Samba. This project reverse engineered the proprietary SMP or CIFS protocol to provide an open re-implementation. And it was tedious and manual work to complete. To automate protocol reverse engineering, we need to identify the methods that are applicable, and they are dependent on the type of protocol. The major protocol types are textual and binary protocols. Textual protocols contain keywords and separator, clearly delimiting where data values are stored, and probably even allowing to identify the meaning of each of the message parts. In binary protocols, the bytes are tightly packed, and there are no separators that help identifying the structure of the message. Moreover, for textual protocols, several sophisticated methods that, for example, employ natural language processing exist, which is not the case for binary protocols. Therefore, we focus on the analysis of binary protocols. And the method that we employ for this is static traffic analysis. There, we only base our analysis on the traffic traces that are recordable from data that is observable in transit. And the advantage of this method is that we require no access to the program of the entities that talk the protocol. This is especially interesting for use cases where the executable binary is not available. This is the case, for example, in malware and botnet analysis for the setup of honeypots for unknown protocols, or to configure smart fuzzers to test the implementation of a protocol where no specification is available. Plenty of related work about protocol reverse engineering exists, and the most closely related to ours are NetSop and Discoverer. NetSop aligns identical bytes in different messages to identify structure and message types, while in our work we align on segments and their similarity. We define segments to be the approximation of protocol fields in the messages. Discoverer, on the other hand, works with segments. They call them tokens, but just of textual message parts. The support for binary parts within messages is only rudimentary, and they leave it open for future work to solve this. In our work, we use a continuous segment similarity for binary data. The goal of our work is to identify message types by clustering of aligned messages. In our approach, we propose the following steps. First, we segment messages into their field candidates that ideally approximate closely the true fields of the messages. Then we determine the dissimilarities between segments, which yields the message format or a hypothesis about the message format. A message format defines where within each of the protocol messages any data or specific header or payload fields are located. From this, we calculate the similarity of messages. This yields a matrix of all pairwise similarities between messages. We can use this as an affinity value for a clustering algorithm. We then cluster the messages to identify the message types. This means that every cluster denotes a message type from the original protocol. A message type defines specific functions that can be triggered during the protocol run. For example, if you want to retrieve the contents of a file storage, then you probably first need to send a message that allows you to log in. The server probably sends an acknowledgement, and then you can request the directory listing for a specific directory. This is replied by the server with the contents of that directory. Each of those message exchanges most probably are of a specific message type, and each message type is of a specific distinctive format. So first we need to determine the dissimilarities between the segments. For this, we interpret each segment as vector of its byte values. We then place those values for the dissimilarities between segments in a dissimilarity matrix, which allows us to have a lookup for the pairwise dissimilarities for all pairs of messages. The challenge here is that the typical distance measures that are available for vectors are only defined within the same vector space. In our case, the vectors have different dimensionalities, so that this distance measures are not applicable directly. Thus, we propose a sliding window interpretation of linear subspaces. We slide the shorter segment S over all possible offsets of the longer vector T and calculate the Canberra distance for each of them. In this example, the most similar overlay between S and T is for the offset of 1. To more formally define this, let's have a look at 4 different examples for the shorter segments S and the longer segments T. We calculate the minimum Canberra distance to determine which of the overlays of the shorter segment over the longer one shows the most similar subpart of the longer segment. The first example selects all the 2 bytes, since S is equal in length to T. The second one, the 0 is contained in T, so we select this one. The third example, the 08 is most similar to the 07. And in the last one, the first 2 bytes are most similar to the bytes of S. And thus, we get the results of the minimum Canberra distance, as you can see below, for all the 4 examples. However, especially looking at the second example, we see that this is clearly not the whole solution, because, of course, 0 is not equal to 0.8, although the distance that we calculated using the minimum Canberra distance is 0. Therefore, we need to take into account the byte values that we needed to omit or ignore, because S did not contain any comparable value for the omitted value in T. We solve this by introducing the Canberra dissimilarity, which is a mixed length dissimilarity with weighted dimensionality mismatch penalty. And it consists of 3 parts. The first one normalizes the minimum Canberra distance to the length of T. The second one penalizes the relative segment length mismatch between S and T. And the third subterm penalizes the absolute dimensionality differences. And the intuition behind this is that having a segment with 2 out of 4 bytes gives us less information than 4 out of 8 bytes, despite in both cases the R for S and T is 1/2. Using this Canberra dissimilarity, we now can compare vectors of different dimensionalities with each other. We place the dissimilarities that we have calculated in the dissimilarity matrix that I introduced earlier, and this gives us an hypothesis about the message format by knowing which segments across the whole trace of the network protocol that we want to analyze are most similar to each other and which ones are different from each other. We now use the dissimilarity of segments to calculate the similarity between messages. And for this, let's have a look at an example of 2 messages, M0 and M1, with the given byte values. And let's assume that they are segmented into the shown segments. And we can now apply a sequence alignment algorithm that determines which parts of the messages are most similar to each other and thus can be aligned to form a common structure. We use the Needleman-Wunsch sequence alignment algorithm for this, which we have enhanced to be able to use the dissimilarities, the continuous segment similarities that we have calculated in the previous step. And sequence alignment also introduces gaps at positions where no alignment is possible. The sequence alignment yields a value that describes how well the alignment could place segments above each other. And those are called the Needleman-Wunsch scores. And we use those scores as measure of the message similarity. We place this message similarity for all pairs of messages into a matrix that lets us identify which pairs of messages are similar to what degree. This now gives us a matrix with all the measures of message similarity that we now can use as an input for a clustering method. We use for clustering the DBSCAN algorithm, the density-based spatial clustering of applications with noise. It's a density-based method, and we chose it because it makes no assumptions about the shapes of the clusters. We need not to know how much clusters we assume to be in the outcome. And it also deals with outliers in that it rather interprets messages as noise than choosing the wrong cluster. The parameters that are necessary to configure DBSCAN can be deduced from the trace. DBSCAN is most sensitive to the parameter epsilon. Intuitively, it's the range around the density cores of samples that should constitute clusters. We propose a method for autoconfiguration of this epsilon, which is specific to our use case. And simply put, it selects the greatest change in the message similarity distribution as an epsilon. The result of this clustering gives us the identification of the message types. We evaluated our method by performing test runs with known protocols. We use known protocols to have a ground truth to compare our results to. We use the well-known protocols DHCP, DNS, NBNS, NTP, and SMB for our evaluation. Since we are not dealing with a binary classification problem, but identify arbitrary many clusters of message types, we need to define a combinatorial cluster quality measure. And thus we define true positives as being all the pairs of messages of the same message type that have been placed within the same cluster. False positives are all the pairs of messages that are of different types but have been placed in the same cluster. And the false negatives are all the pairs of messages that are of the same message type but have been placed in different message clusters. Using those values, we now can calculate the well-known cluster quality measures of precision and recall. To initially obtain segments at the beginning of our process, we tested multiple methods, and two of those are T-Shark and Nemesis. T-Shark uses the information from Wireshark dissectors to determine the true field boundaries and yields segments that are perfectly resembling the fields of the protocol. This is the ground truth and allows us to test our protocol under optimal circumstances. The second segmenter is Nemesis, which is applicable to unknown protocols where, of course, no dissectors are available, so T-Shark cannot be applied. Nemesis is an heuristic approximation of field boundaries for binary protocols. We proposed Nemesis in an earlier work. The evaluation of our protocols show that using segments yielded by T-Shark, we can almost always achieve the perfect precision of 1. And also the recall is quite reasonable, with the only exception of DHCP, which is a quite complex protocol. T# denotes the theoretical optimum that our approach can achieve, given that the segments perfectly match the fields of the protocol. Using Nemesis as a heuristic that is applicable for actually unknown protocols shows that the precision and recall values are reasonable compared to the theoretical optimum, and we are only marginally worse than that. Comparing our method to the previous method of NetSub, which aligns byte-wise and also determines message types from this, we can see that we outperform NetSub in both dimensions. This evaluation showed that for the theoretical optimum of T#, the segment dissimilarities actually shows differences between the field types, and that this is suitable to reveal the message similarity. On the other hand, in cases where no dissector is available and we need to resort to a heuristic method, Nemesis shows that this segmentation is also possible without knowledge about the protocol. We implemented our approach in a proof of concept we call Nemetil, the network message type identification by alignment. It contains our novel method for message type identification and works with unknown binary network protocols. It does not require the analyst to manually select any parameters. We interpret binary data as feature vectors and calculate a vector distance for unequally sized feature vectors. For sequence alignment, we use an optimized version of Needleman-Wunsch called Hirschberg alignment, and we apply it together with the clustering by DBSCAN, for which we proposed the epsilon auto-configuration. Thank you for your interest in our work. If you want to have a look at the code of our proof of concept, please go to the GitHub page of the Institute of Distributed Systems of Ulm University. You will find the link to this GitHub page in the slides. And also, if you have any questions, you find ways to contact me in the slides, for example, via email or Twitter, and I would gladly reply to any questions you may have.